Hello, everyone, and welcome to the Gravity Max live stream. So, today we will be discussing um, the qualities of a habitable planet. And today I'm here with Sebastian,
Hey, everyone.
and we have another guest here today. His channel is Daikaiju Productions, and he has a channel here on YouTube, and he makes some pretty cool stop motion animations. And you should check it out. Link in the description.
Hello, peoples.
So, should we just get right into it, or should we give it a couple of minutes?
Yeah, we can give it a couple of minutes. So,
All right.
Today, November 2nd, we are in the wake of Halloween on Thursday, and we have a little...
Which is why there's a pumpkin on the bottom left. Yes.
Yeah, so... we hope you enjoy this stream. If you want, go grab some Halloween candy to snack on. Because, the streams tend to be a little long, so grab some Halloween candy if you got any, if you want a snack. And another interesting, it isn't really a holiday, but event is that tonight will be the end of daylight saving time for 2019, and it'll all go back to normal, basically. So we get an extra hour of sleep tonight, which is nice.
Yay!
Yeah, so... Yeah.
Yep. So we got a great topic for you guys today.
Yeah.
Which we'll introduce in a little bit, but let me tell you, this is a good one. And I'm
Yeah.
glad we have Daikaiju Productions here to discuss it with us.
Yep.
Because he's going to give a very interesting angle on this, which we're going to see later on in the stream.
Yeah. Thanks for coming on the show.
Yeah, thanks for being here.
So, so I guess we can get started. First slide.
Here's the first plug.
Yeah, plug number one. Visit the Gravity Max website. We don't really have much there, but I have a video suggestions form and a, contact me form. So if you want to, say, hey, I like your videos, then you can do that. Or if you want to say, hey, can you make a video about this? Then you can do that there too. But I also check my comments usually. So, it's not anything revolutionary on the website. And you should follow Gravity Max on social media because I put updates about our stream. I say reminders and stuff like that. So you should follow that. And then I should really change this from available this November because it's it is November now. So I need to decide when in November. But this is my book, my sci-fi book, A Truly Dead Rock. It will be available in a few weeks. I'm shooting for Thanksgiving to capitalize on that Black Friday. I almost said
Black
market
on Black Friday.
Black market books. No, trying to get that Black Friday. Yeah. So you should pick up a copy.
I'm so ready for this book. I am so ready for this book. You don't understand. I've been just in anticipation. I've been sweating for 2 years straight. I need this book in my home. I'm the first in line to receive this book, available on Amazon this November.
Yeah. Thank you. It's a fun book. It's my first book, so it would be pretty great if you went and got a copy. So it'll be out Thanksgiving, and if you want to get it, because it'll be cheaper during the first few days, and then the price will go up. So yeah, it'll be a release sale. So yeah. So qualities of a habitable planet. This is our topic.
What allows for life to be on a planet?
Yep. So,
why do humans exist? Where did my pants go? All these questions will be answered today on stream.
Wow. I'm really fascinated to hear the answer to that last one.
Well, let me tell you, it might have something to do with our next slide. Class M planets.
Okay. Class M planets.
So, little backstory on this. If you've noticed, in pretty much all of our streams so far, I've referred to habitable planets as Class M planets.
Uh-huh.
And this, if for those of you who didn't understand why I was calling it this, Class M planets, I thought that this was what NASA used to designate habitable planets. It's actually what Star Trek uses, which is what I found. So always remember to watch what you say on the internet and do your research.
Yeah.
This did inspire a large section of this live stream today.
Yeah.
Because in the next 10 to 20 slides, we have all the listings of the Star Trek planet classifications.
Yeah. It's funny. I had never heard the term Class M planet before. I had heard M star because it's the OBAFGKM. So M is like the red dwarf stars, but I had never heard of Class M planets. So I was like, so what do you mean by a Class M planet? And he's like, oh, it's habitable planets, what NASA uses. And I'm like, really? I did not know NASA used that.
Yeah, when Max said that he didn't know that, then I knew something was wrong. Then I went and looked it up.
Yeah. Anyways, it is a pretty good term. The classification system, while it may not be the most like objective scientific classification system, it is good for just like human experience and like visualizing the classes in your mind, because I mean that's the point of media. So Star Trek as a science fiction show isn't going to give you like crazy, like ridiculous classes, because typically astronomy is filled with misnomers and like names that you don't think are really good. But here, this classification system probably makes more sense because it was made for people to understand.
And by the way, I'm going to continue calling habitable planets Class M planets.
All right.
I'm not going to stop just because it's from Star Trek.
Yeah. Okay.
I think it's a good just little nickname. You know?
That's fair. Yeah.
I don't think similar to.
Similar to what?
It is like it's not that far off from NASA's actual idea of habitable planet zone or something.
Mm-hmm.
Are the definitions?
It's not completely. It's like based off of it. It's not the actual term, but it's based off similar theory.
Yeah. So this is like a semi-scientific term from Star Trek. Should we go to the first class of planet?
I can take these guys.
Okay, these are all alphabetical, by the way.
So, yes. So, first off, we have Class A, B, and C. These are typically small, young planets whose class depends on their age and solidity of their cores. A real-life example is Mercury, which here I have and yes, it's pronounced GIF of Mercury just spinning, as most planets do. Mercury would be considered either an A, B, or C planet. I'll pull that specific thing up later. But these are just like small and relatively young planets. Right here. Yeah, Mercury is a class.
Oh, sorry. I think you're cutting out a little.
Of that classification.
You're cutting out a little. Could you repeat that last sentence?
Oh, did I cut out?
Yeah.
Okay. I was just saying that Mercury is your best real-life example of what a class like A to C planet would be.
Okay. Yeah. Great.
Let's head over to the next one.
Okay. Yeah. Sure. Class D planets.
Okay.
So.
Jacob, you want to take this one?
Oh yeah.
Right. Our Class D planets are planetoids like asteroids and submoons. One example would be Vesta, which is on the slide in the picture. Next one is. Should I take this one? Yeah.
Oh, the next one. Oh, E, F,
yeah,
and G?
sure, if you want.
Okay. The next one is Class E, F, and G planets, which are like proto-Earth-sized planets, which their class also depends on the age and solidity of their cores.
So yeah, the picture we have up here is like when we say proto-Earth, that's kind of like when Earth was getting formed.
Yeah.
So right here we have kind of an illustration of what Earth might have looked like while it was getting formed.
Mm-hmm.
But again, class E, F, and G really just refers to their size and their age.
Yeah, so is this kind of like Earth in the late heavy bombardment stage when it was just getting like hammered with asteroids?
Yeah, before the Hadean era.
Mm-hmm.
But yeah, basically when everything was just death.
Okay. Yeah, that's
so,
always fun.
All right, heading over to the next slide.
Uh-huh.
Class H planets. Okay, ladies and gentlemen, right now I'm saying Dune is my favorite book only because A Truly Dead Rock has not come out yet. But Dune by Frank Herbert is my favorite book right now. And right here, I have a depiction of the main planet in Dune called Arrakis. Arrakis is a desert world, and it fits perfectly into the Class H category because Class H planets are harsh desert worlds.
Mm-hmm. I mean, I guess it's fitting for the book name Dune because, I mean, the book name makes sense because it's like sand dunes.
Exactly.
Also, I remember I've seen a few like cover art pictures for that book. Isn't there like a giant worm thing that like lives in the sand?
There is. Shai Hulud, Guardian of the Spice.
The Spice.
But you're gonna have to read the book.
Yeah. Okay.
Isn't that like the sci-fi series where they don't have computers?
I don't think it's that one. Dune is like weird because it's super far into the future. It's like 10,000 years into the future, or like 8,000, I would guess. But they've kind of like fallen back to medieval times.
Yeah, that's a fun
So they
trope.
have like kingdoms and such, except it's on a planetary scale.
Yeah, that's always a fun like little trope. Just the like really old ancient civilization that is like in a like weird state, backward state, you know. So yeah, that's pretty cool. Another example I think would be, I can't remember. Tatooine from Star Wars, right?
Yes.
Yeah.
Yes, definitely.
Cool.
Jakku.
Oh, and Jakku, yeah.
Jakku's not.
Should we go to the next slide?
Yeah.
Cool.
All right, I can take these.
Okay.
So here's kind of the issue with this and some of these classifications in this category. There's Class I, Class J, Class S, and Class T. They're all different classifications of gas giants. But Max, do you want to explain why that isn't actually accurate?
Yeah,
because they're all referring to size.
Yeah, sure. So I forgot the order. So this is supposed to be kind of a size order of these gas giants. So what's the order from biggest to smallest for these classes?
It goes J, I, S, T, if my memory serves.
So wait, or you mean I, J, S, T?
J, I, S, T. With Jupiter and Saturn being J. Being J.
J, I, S, T. But this one, I says Super Jupiter, though.
Yeah, exactly, because Jupiter is J.
Oh, you mean... Oh, you were going up, not down. Okay, so J-I-S-T. Okay, so basically...
Oh, yeah, sorry.
Oh, yeah, it's okay. I was just a little confused. Basically, the problem here is that when it comes to gas giant size, none of the gas giant planets actually get any bigger than Jupiter, even though some are more massive than Jupiter. And this is just a density thing. So it basically, Jupiter's size is like this critical mass for gas giants where as you add mass, it really can't support itself and get any bigger. So it just stays the same size and you just add mass. And this is because once you get to these scales, you're really forming like a tiny star. The smallest stars, brown dwarf stars, which are like barely even stars, are basically these like objects that are about 13 times the mass of Jupiter, but they're still about the same size of Jupiter, maybe a little bigger, and they undergo deuterium fusion, but not full hydrogen chain fusion like in the sun. So they're like these weird class of objects, but as Star Trek is a sci-fi show and it's like for people, sometimes it's kind of hard to understand the difference between an increase in mass and an increase in radius. So they just kind of say these planets are bigger in radius and size when they would really only just be bigger in mass. So it's just a little bit of I don't know, it's only a small inaccuracy, just a little bit of confusion, just to make things simpler, I guess, right?
Yeah.
Yeah. So class I. What is class I?
Class I is another. Oh, sorry. What were you saying?
Class I. Just like a little description. So it's just like super Jupiters, right? Just what's the mass
Class
range?
I just threw a picture in of like a theoretical super Jupiter, but
Mhm.
again, as Max just said, like Jupiter's kind of at critical mass.
Yeah. Yeah, this is like a what is it? An artist rendition of a exoplanet, I think.
Yeah.
Um
Yeah.
of what
So
a
yeah,
super
let's we can head over
Yeah.
to Class J.
Okay. Class
So
J.
yeah, Class J planets are basically the gas giants we all know and love. The two most famous being, of course, Saturn and Jupiter.
Yep.
And in the Star Trek universe, they are the smallest of the gas giant classifications.
Mm-hmm. Which is odd. What do you classify like Neptune as?
I would guess that would also be a J.
Mm-hmm. That's interesting.
It is.
Because Neptune and Uranus size objects are often called ice giants instead of gas giants. Like because of their size, it's mostly like ices instead of just like hydrogen. They've got a lot of like ammonia and water and other things, which we'll talk about later actually, as their uses as solvents. But basically, I would think that they would get their own classification, you know.
Mm-hmm.
But again, that's just one of the little flaws of this system is that it's more for show. It's for presentation rather than for describing the physical world. So I will go to the next slide.
Okay, can I say something real quick?
Oh yeah.
Okay, so in the background, if you've been hearing frantic clicking, that's been me trying to pull up the Wikipedia page. That we used for all of these classifications, but we also like checked it with like other official Star Trek canon sources. But the Wikipedia page that we were for this actually got deleted 2 days ago.
What?
Like, yeah, what are the chances?
Wait,
I'm checking the deletion log.
Was it inaccurate?
Yeah, try and search for it. I'm checking the deletion log right now at 12:34 on Halloween.
Oh my god.
They deleted the page we were using.
I feel like oh my gosh, does this mean this whole part of the video is just inaccurate or
No, it means that I'm looking into the deletion notes and they just merged it with another article. So I'm just using that other article now.
Oh, okay.
But I just thought it was hilarious how 2 days before we decide to make an entire live stream on this, they delete it. Like, what are the chances?
Pretty crazy.
So no, everything we have is still accurate because
cool.
we also checked it with those other canon sources. All they did was they merged it with
another
a different a different thing.
Okay. Yeah, I just wanted to, make sure that we were still being accurate because you don't want to get
definitely
a ton of Star Trek fans mad at us.
Yeah.
Yeah. So Class K objects or planets. What would you say about Class K planets?
Jacob, do you want to take this one?
Sure. So a Class K planet, it's like Mars. It's a barren world with no native life.
Mhm.
They don't have breathable atmospheres, but have reasonably tolerable gravity, so they can be colonized with atmospheric domes or by terraforming the planet, which would then make it into a Class M world.
Mhm.
So Mars is a good example. That's what's shown in the picture, because you could theoretically put a settlement there if you like had oxygen and whatnot contained within it, or if you had the technology, you could make an atmosphere and terraform it, which we'll get to in a later slide.
Yeah.
Mm-hmm.
Cool. Okay. Class L planets. So this looks like This looks like terraformed Mars. Is that what this picture is? Like a
No, this is just. I just looked up whack planet, and this is what came up, because Class L planets are barely habitable worlds with primitive ecosystems.
Huh.
So something like this, where it's either all ocean or just harsh desert, could only sustain like a very primitive ecosystem.
Yeah.
You know?
Well, that's interesting. Because this is actually a picture of a terraformed Mars. If you notice at the top left, you see Olympus Mons. You see that island there?
Oh yeah.
Yeah. And you can see the boundary, the border, how Mars has like the entire northern hemisphere is like slightly lower than the southern hemisphere. So that's pretty interesting, because I think Mars, as it currently is a Class K planet, as you terraform it, before it got to M, it would pass through L.
It would pass through L, exactly.
Because, like, before it can, like, support complicated life, it could only support, like, bacteria and stuff. And that would kind of be what that's this picture. That's what this picture is right now, because it's not green yet, but it's got an atmosphere, it's got water. So that's pretty interesting.
Do you want to acknowledge that? Oh, yeah, go ahead, Jacob.
You said you searched up whack planet. I just searched that up, and one of the first things I found is a picture of Jesus Christ with the head of a mountain lion.
What?
What?
That is so random. That's crazy. Whack planets.
What?
I gotta look this up.
It's Jesus Christ.
I just looked it up. It's completely true.
I will look up whack planets. Whack planet.
What is this? I want everyone that's watching right now to search up whack planet.
Yup, it's right here. It's like a bobcat or something. What is this?
Is this like a band?
Yeah,
this looks like a band.
It's a band.
It is a band. I knew only a band could come out with something this strange.
I am bemused, honestly. I am just in shock here. Anyways, that's pretty interesting. So
I was just saying if we should acknowledge chat.
Oh yeah? Okay. Let's take a look at the chat. So, what comments are in particular? We've got.
Sorry, what'd you say?
What comments in particular? We've got missing music. I don't know who that is, but thank you for watching the stream.
I do.
Okay.
So thank you for being active in chat.
Mm-hmm.
So shout out to Missing Music.
Yeah.
Again, I share your enthusiasm for A Truly Dead Rock. I am so ready for this book. It's ridiculous. Yes, I do completely agree with you. What awful timing for that Wikipedia article to be merged with the other thing. And it got merged with the official Star Trek Wikipedia page, if any of you are interested. It's now under planet listings, I believe.
Mm-hmm. That's cool. So thanks for watching the stream, Missing Music, and I'll have to ask Sebastian who you are at the end of the stream. So should we go to the next slide?
Yeah, let's do it.
Cool.
So this is kind of an obscure thing. I'm joking. It's a Class M planet. This is what I've been saying in all of the streams. Of course, a Class M planet is a life-supporting planet within the habitable zone, and we're going to talk about like the Habitable Zone and the Goldilocks Zone later on in the stream. So basically, it's a planet that can sustain life, has a rich ecosystem. In the Star Trek universe, specifically the term M comes from the Vulcan language. It's derived from the word Minshara. But basically, Class M planets are said to possess an atmosphere composed of nitrogen and oxygen, as well as an abundance of liquid water necessary for carbon-based life to exist. This is interesting because here they're determining water as a universal solvent, but we're going to talk about some other alternative solvents later on.
Oh, I found out who it was.
Extensive plant and animal life often flourishes, and often a sentient race is also present. So, of course, the only real-life example of a Class M planet we have is Earth.
Or Dewey.
And, like, that hits every category. Concerning sentient race. Well, yeah, basically sentient race is it. Because NASA has been looking at, like, habitable planets, like, per se, but some, like Mars, need terraforming. Others have all the elements of Earth, but for some reason, or at least we haven't observed any life on them. So that's a mystery for another day.
So a Class M planet it's for the purposes of the show, it's just to have, like, throwaway Earth copies, right? Just like just like, here's a society, it's pretty much Earth, but then the society's weird. Like, I don't know, they have a weird, like, gerontocracy or something where the leaders are just whoever's the oldest person on the planet, instead of, like, a democracy or something. Just, like, to showcase societies on planets that are pretty much just Earth, right?
Yeah. They also use, like, Class M planets for, like, where the Vulcans came from, where the Klingons came from.
Yeah.
All that.
That's cool. So Class N.
Jacob, do you want to take this one?
Sure. So basically, Class N planets are rocky planets with extremely high temperatures on the surface and a reducing environment. I'm not sure. Do you know can you explain what a reducing environment means?
A reducing environment. Well, if it's talking about chemistry, then it might be the process of reduction, which is basically when an atom gains electrons. And I guess that could make sense because Venus is a very acidic, like, it has sulfuric acid in its atmosphere, which is like, I think it's, I don't know what it is exactly. Sulfuric acid. What's the chemical formula of sulfuric acid? I'll look that up. But yeah, it's got sulfuric acid. What?
It says in the description that there's thick atmospheres containing carbon dioxide and corrosive sulfides.
Yeah. So
I think that's probably it.
Okay. Yeah.
It could also just mean that, like, generally reduces the chances of life existing on planets like these.
Yeah.
Because, like, these are definitely not habitable.
Yeah.
Maybe even outside the realm of terraforming, but we're going to talk about that later.
Well, it's actually interesting because a lot of scientists argue that Venus would be easier to terraform than Mars. But
because of the clouds and stuff?
Well, it's basically because if you were to basically build a cloud city, like from Star Wars, at like 50 or 55 kilometers up in the atmosphere, it would basically, you would still need an oxygen mask to go outside because it would be, the atmosphere is purely carbon dioxide, but the temperature would be appropriate. It would be like a high 80. And the pressure would be appropriate, maybe a little low, but it would be fine. And you would literally only have to watch out for sulfuric acid rain and just not go outside when that happened. So I think this is a case for Star Trek. It's another example of how this is artistic liberty for the show, which is basically it's saying on the surface it looks like, just objectively, like if you don't go into it that much, it looks like Mars would be easier to terraform than Venus. But if you, like, really research it, you see that Venus is actually easier. But of course, the like depiction of a hell world compared to just like a frozen barren planet that can be unthawed, you kind of think, oh, obviously the Martian type planet could be terraformed. So it's interesting. Yeah.
Next, we just need to have a movie with Matt Damon escaping from Venus.
Oh my gosh, yeah. That would be pretty interesting. I would like to see that. The Venusian. What?
What'd you say, Jacob?
They sent anything to Venus? Like, they've sent rovers to Mars. Have they sent, like, drones or something?
Yeah, everything that we've sent to Venus has destroyed in the first, 10 to 15 minutes.
Yeah, and basically the problem there is we sent them down to the surface. We sent nothing that had, balloons on it. So we've sent probes to the surface of Venus, and the record, I think, of survival is, 2 hours or something.
No, it's actually less than an hour.
Really? Yeah, so it's just not a good place, the surface. The surface is bad, but it's kind of like you can imagine it like the ocean. The ocean's really habitable up at, the surface, but if you go too deep, then the pressure will, crush you. Like a submarine, if you don't have enough pressurization in your submarine, if it can't handle it, it'll get crushed. So it's when considering Venus, people often look at the surface, but looking at the surface is like looking at the bottom of the ocean and trying to consider habitability. It's just not a fair comparison,
That's a good analogy.
Yeah, thanks.
So would the atmosphere have buoyancy or something that would allow a potential city to just float there, or
the atmosphere is fairly buoyant. Basically, the density of carbon dioxide is around 2 grams per liter, whereas normal air is 1.25 grams per liter. So on its own, normal air is buoyant. But of course, it would be better to just use helium, which has an even lower density. And the best buoyant thing to use for Venus would actually be hydrogen. Now, I know hydrogen blimps does not sound like a good idea, but that's just on Earth.
I joked in the last stream about that.
Yeah.
How hydrogen would be a great fuel for blimps.
Yeah.
That disclaimer, that is a joke.
Yeah, that is a joke. Basically, hydrogen blimps are only a problem on Earth because Earth has a atmosphere that is 20% oxygen. So your hydrogen.
Way to go, Earth.
Yeah, come on, Earth. Oxygen is actually a very dangerous substance if you think about it, but we just don't think about it. So hydrogen would actually do very well on Venus, where its atmosphere is just carbon dioxide. It would not burn, and you could use it as a buoyant force to keep your city afloat. So yeah.
Let's head over to the next one.
Cool.
So we got Class O and P planets. So right here, we've included a picture of Hoth from Star Wars.
Mm-hmm.
If you remember anything about that, that's where they famously took down that AT-AT by wrapping the cords around its legs.
Yep, and it's been referenced hundreds of times in pop culture. I think Avengers Civil War, right? Spider-Man was like, have you ever seen that really old movie, The Empire Strikes Back? And then he knocks down Ant-Man, who's giant, and then
But the point of Class O and P planets are planets covered almost completely with water, which is a Class O, or water ice, which is a Class P, which would be Hoth. And again, in Dune, my current favorite book, only because A Truly Dead Rock has not come out yet. The planet that the main character comes from could be considered a Class O planet. It's called Caladan, and it has a lot of water, which is kind of like a cruel irony.
Yeah, that's really interesting. I was about to say that then
he gets stranded on a Class H planet.
Yeah. Oof, that's
pretty much the exact opposite.
That's rough. So I don't know, his ship went down or something?
Well, I don't want to spoil the entire book, but basically his father is involved in politics, and that can cause trouble for everyone around them.
Imagine being
So that's
involved
where I'll
in
leave that.
politics.
Wow.
Yeah, politics, dangerous stuff, but important as well. That's pretty interesting. I like that they made him come from a water world and send him to like a desert world. I mean, that's your total like in the hero's arc or whatever, hero's journey. That's total like status quo and then like breaking of the status quo. You know, just like send him to the opposite of what he's used to. So that's cool. Should I go to the next slide?
Yeah, let's do it.
Cool. So
you want to take this one, Max?
Okay, so I don't know these as well as I think you guys do, but if I remember correctly from our discussion, Class Q was like a planet that had odd weather and climate and just dangerous events. Like there's a hurricane on that planet right now.
Yep.
Yeah, so, and I think this could be caused by a planet either being around a binary star or by having a high eccentricity in its orbit, which basically means that not most, okay. Technically, none of the planet's orbits are circular. They're nearly circular, but not completely circular. They're all elliptical to some degree, but I'm guessing a Class Q planet, if it were to have a high eccentricity, it would be very elliptical, and it would swing from very cold reaches of its solar system and down close to the sun in a hot part of the solar system, and that could cause pretty bad weather. Also, tidal locking could cause pretty bad weather, but what does it say officially?
Yeah, you basically got it.
Okay.
Yeah, it's just planets with, and I don't want to overuse this term, but whack orbits. This is truly a whack planet.
A whack planet. I mean, it just looks whack. Like the water color, like instead of choosing like the dark blue of water, they chose this weird like cyan, like bright radioactive colored water for this planet.
What's the hex code of that color?
It's probably about OOFFFF. Not exactly, but maybe a little darker. But
close enough.
Yeah, what did you look up to get this planet, like on Google Images?
I think Jacob did this one. Jacob, how'd you get this? I
think I just Googled Class Q planet.
Okay.
Nice.
That's generally the best strategy. Okay.
They somehow made the water like a dark cyan. I'm not sure how that's a color, but it is.
Yeah, they made it a dark cyan, like OOCOCO maybe, for hex code, for the hex coders out there. Yeah. So.
No way.
What?
Okay, nope, never mind. Sorry.
Should I go to the next slide?
I was looking at and I thought that it got moved to, like, the original article got moved to a sub page coming off of the main Star Trek page, and then I thought that page got deleted.
Oh my gosh. They can't just delete the entire Wikipedia page for Star Trek.
Star Trek never existed.
Oh my gosh. Honestly, could you imagine if Wikipedia just selectively, just if they didn't like something, they could just delete all the articles on it, and then a lot of people would actually believe that it just never existed. Like,
Mandela effect.
Yeah, because if it doesn't show up on Wikipedia, a ton of people would just be like, "Oh, I don't know, it's not on Wikipedia, it's not real," which is interesting. I guess that's some credence to the teacher's constant insistence on like, no Wikipedia, never use Wikipedia. It's really funny because they were really big about that in middle school and elementary school, but now my high school teachers are like, Wikipedia is a pretty good resource, just don't cite it. They're like, you can go there, get some background information, but like you should go to some real sources too. And I'm like, thank you for the moderate perspective. You know?
Yeah. We have a question in chat.
Oh, yes.
The question is, So how would you suggest sending something to Venus without it landing on the surface? How do you think the outcome would change? Would it stay intact?
Okay, yeah. So basically, what you would do here is, as a planet, or sorry, as a probe is entering, like, is going down into a planet, they always deploy a parachute. For Venus specifically, with Mars, they need a parachute and rocket boosters because its atmosphere is too thin. But with Venus, you could get away with just a parachute, and they use that parachute to slow its descent enough so that it doesn't like hit the surface and just break and shatter like a computer dropped off like a 10-story balcony, right? So you would pretty much just, I guess, need a bigger parachute so that it would slow down sooner, and then you could inflate these hydrogen balloons, presumably, that you would have kept in like liquid hydrogen canisters, which would kind of be a dangerous proposition for space travel. So maybe instead you could use helium. That might be safer, because space travel has a lot of explosive reactions, so you would have to be very careful with your hydrogen there. But once you're actually on Venus, you're pretty safe using hydrogen. So I think that's kind of how you would go for it, you know?
Yep.
Yeah.
Yep. I think you got it on that one.
Cool. Okay. I mean, and I'm no, like, NASA rocket scientist, but I do hope that if NASA uses that idea, they pay me royalties. I expect royalties, NASA. Anyways.
All right, let's hit the next one.
Oh, yeah, sure. R.
So we got Class R planets.
Nice.
R stands for rogue, which is what these planets are.
Nice.
Rogue.
Rogue
These
planets
are
interesting.
defined as a rogue planetary body, which is one that does not orbit a star but drifts freely in space.
Mm-hmm.
So this is a planet that is just yeeting throughout the galaxy
Yep.
with no qualms whatsoever.
Exactly.
With any stars, nothing like that.
And this is an official planet classification. There are actually there is like an actual official definition for a rogue planet, and it's exactly that. Because that's more concrete. Yeah, that's more
What were you
concrete.
saying, Jacob?
Doesn't that fall
Oh,
under the definition of a planet, though?
What? Sorry, what were you
Doesn't
saying?
that fall outside the definition of a planet because they have to orbit a star or something?
Well, yeah, that's the thing. This is for exoplanets.
Yeah, that's true, actually.
The definition of a planet, strictly speaking, is it has to orbit the sun, right? It specifically has to orbit the sun. That's why all of the planets we find around other stars are exoplanets, because an exoplanet is a planet that does not orbit the sun. So I think it fits the definition of exoplanet, or it has its own definition, rogue planet. You have to be kind of...
No, Jacob is right. Even the definition of an exoplanet is a planet which orbits a star outside of our solar system. So,
But that's...
actually, technically, a Class R planet is not even a planet.
Well,
guys, we are making discoveries.
Well, okay, but here's the thing. What if you look up the definition of a rogue planet? Because if it just says in the definition, it's a small body drifting through space, then there's your definition.
I'm looking that up as well. Fine, rogue planet. Okay.
At that point, it would be an asteroid?
Well, no, because if it's in hydrostatic equilibrium, which is if it's like rounded itself into a spherical shape, then it's not.
Here we go.
Yeah, then it's no longer
a rogue planet, also termed an interstellar planet, nomad planet, free-floating planet, unbound planet, orphan planet, wandering planet, starless planet, or sunless planet.
Imagine having that many nicknames.
Sorry, what were you saying?
Imagine having that many nicknames.
Yeah, I can. My name is Sebastian. Come on. I have like 30 nicknames.
Yeah, that's true.
Anyways, a rogue planet is a planetary mass object that orbits a galactic center directly. So, like a black hole at the center of a galaxy is the only thing it orbits.
Yeah.
Or a nuclear star cluster.
Yeah, and that's a pretty loose term for orbit because it's just it's a whack path that it takes through space, constantly being adjusted by nearby stars. And yeah, basically a rogue planet. It's left its sun. It's drifting through space for billions of years. So it's basically frozen over, just cooled down like a hot potato taken out of the oven. Cooled down to the temperatures of interstellar space, which is like 3 Kelvin. So you would not find life here.
Yeah.
Other than
So for a real
under
life
frozen ocean.
example, we have the well-known planet of CHA 110913-773444.
Honestly,
Everyone
it's a
knows
household
that planet.
name. Yeah, household name.
Household. Yeah. So yeah, that well-known planet is our closest, our best possible real-life example
Of a rogue planet. That's really interesting. I wonder how they found that planet, because typically scientists find
tell you.
exoplanets by measuring how they affect their star. And since a rogue planet, by definition, does not have a star, it's like, how do you even find something like that?
It was discovered, so I'm not going to say that name again. I'm just going to call it Cha, because those are the first 3 letters in its name. So Cha was discovered in 2004 by Kevin Luhman and others at Pennsylvania State University using the Spitzer Space Telescope and the Hubble Space Telescope, as well as 2 telescopes in Chile.
So it could have detected infrared.
That's all it says.
Well, I guess that's a story for another time. But yeah. So that's interesting. Rogue planets, they're an actual thing. So this is a pretty scientifically grounded classification from Star Trek. So I'll go to the next one.
Yeah.
S.
Jacob, you want to talk about Class S planets?
So, Class S planets are gas giants which are smaller than Class T and are larger than Class J. As we talked about this earlier, how this isn't really a real thing because Jupiter is essentially the largest that they get in terms of radius.
Yeah.
So basically, in the show, these would be larger than Jupiter and smaller than Class T planets, which are even larger than this. And in the real world, they just don't exist.
Yeah. They could, just be more massive, but the same size. But, yeah, so that's interesting. That's just a simple one, you know? So less scientifically grounded. And then T. T is just more, right? More massive than S.
T is the largest class of gas giant.
Do they say
it's known as an ultra giant?
Do they say how massive they are in Jupiter masses?
I'll try and tell you.
Okay, because here's what I'm thinking. These might be how Star Trek decides to deal with the concept of a brown dwarf star. Because if it's anywhere above 13 Jupiter masses, then it would technically be a brown dwarf star instead of a planet. It would no longer be a planet.
A Class T planet is a gas giant classified as a large ultra giant, and it has a diameter 50 million to 120 million kilometers in diameter, with an age of 2 to 10 billion years. Earth years.
I'm pretty sure 50 million. Let me see. So 50 million kilometer radius is the small end, 120 is the large end.
Diameter.
Oh yeah, sorry. So Jupiter. Okay. So it's in kilometers. That's interesting because Jupiter's diameter is 140,000 kilometers. So this would be smaller.
Jupiter would be way smaller.
Well, no, Jupiter said 140,000 kilometer diameter.
Yeah, and I said 50 million to 120 million.
Oh my gosh, million.
Yeah,
dude,
that's kilometers.
That's bigger than the sun. Wait.
Exactly.
Canis Majoris radius. VY Canis Majoris is one of the biggest stars in existence.
It's a unit.
It's an absolute unit. And I'm just gonna see its radius. Okay, it's a bit bigger, but it's it's here. I'll look up just solar radius. Solar radius. Okay, so Okay, so the sun is it's not as big as these planets apparently, which I don't trust. I don't trust
I
it.
don't trust that.
I think Star Trek is probably not very good at dealing with gas giant star boundaries. They don't respect the boundaries and they don't know the physics of gas giants. But you know what? That's okay.
The writers, when they're making the classification, they make like Class J be like the smallest, and that's Jupiter, and then they're like bigger.
Yeah.
So they make Class I, and they're like bigger. And then they make Class S, and the head guy is like, guys, what if we took Class S and made it bigger?
Yep. Yeah.
And then he got fired, but not after they stole his idea.
Not after they
But
put
it was
it
at
in.
Class T where they stopped.
Yeah. So, this part, all the gas giant stuff, take with a grain of salt. Other than our critiques, because those are the scientific critiques. Anyways, so
let's
next,
go over to Class Y.
Class Y.
Jacob, talk about Class Y planet.
Okay, so Class Y planets are basically demon worlds.
Doom soundtrack.
Yep.
Yeah.
Yeah.
And by demon world, I do not mean the public school restrooms. I mean like the entire planet is on fire. Like, so basically, it's unrecognized surface conditions, which are hostile and lethal to humanoid life. So if life develops on these worlds, it's usually like they take bizarre forms like crystal or rock. So like the Thing from Fantastic Four would live on this planet.
Yeah.
Liquid or gaseous physical states, or incorporeal, dimensional, or energy-based states, which I don't think is scientifically possible.
Yeah.
No. That quote that it's life would take an incorporeal, dimensional, or energy-based state is a direct quote from the Star Trek official website.
Oh, wow. Yeah.
So, yeah, if anything was to exist on this planet, it would either be a living crystal or rock, a living liquid, a ghost, some extra dimensional being like
a living nothing,
Bill Cipher or something, or literal just energy.
Yeah. So that's actually interesting because I was about to ask, what's the difference between this and the E, F, and G classifications? Because both of those were like hot magma, like Earth 5 billion years ago. But so I guess this is kind of like E, F, and J, but if you somehow made a life form to live there.
Yeah. Exactly.
So now
also like E, F, and G are developing. This is I'm pretty sure this is just like
this is end phase. This is
state.
Yeah. I want to look up examples of Class Y planets in Star Trek.
Yeah.
Here we go. So yeah, in the episode Star Trek Voyager, titled literal just Demon. That's the title of the episode. They were in the plot of the episode, they were forced to land on a Class Y planet in the Vaskin sector after detecting desperately needed deuterium on the surface.
Ooh, rookie
they
mistake.
then discovered that the deuterium contained a biomimetic life form called the Silver Blood, which duplicated the crew and ship.
What?
That is awesome.
Biomimetic.
They found a mimic.
They
just found a straight up mimic on this random planet. That is
so weird, but I mean, I guess you got to keep a show entertaining, right? When you run out of interesting things in science, you just kind of take a liberty, go into fantasy a bit. But yeah, that's pretty interesting. So should I go to the next?
Star Trek Secret.
Should I go to the next slide?
All right.
Should I go to the next?
So going over to the next slide.
Yeah. Oh, can I?
Class X. Oh yeah, go ahead. Go ahead.
So this is interesting. Class X and Z planets. They are basically worse versions of Class Y planets, if you can imagine that. Class Y was already pretty bad, and then X and Z are worse.
And we made it badder.
Worser. Yeah, and basically, here's my theory on the naming here. The letter Y isn't really as scary of a letter as the letters X and Z. So I think they kind of went with X and Z are really scary letters, so we'll just make them worse versions of Class Y. You've got to have that naming system. I mean, the letters X and Z are like the most scariest things in a name. Think about it, right? You've got Planet X. Always sounded so menacing, right? You've got World War Z, right? That movie, such a like scary, menacing title. And then you've got iPhone X. I mean, those two cameras scare me so much. And yeah, that's my theory on this class, right?
We've got Generation X.
Generation X. Are they boomers? Are they millennials? Z. I have no idea. I'm scared.
Yeah. We're at Generation Z. What's even going on?
Oh my gosh, Generation Z, the most frightening.
They're not millennials. They're not boomers.
Generation.
Man, these are the two scariest generations.
Yeah. Anyways, yeah. So, what would you find on a Class X or Z planet? Like, how do you get worse?
Let me tell you. Let me look up an example.
Okay.
Appeared in an episode.
Okay.
Probably fire.
Class. Okay, here we go.
Okay.
So it has not been shown in an episode. Only Class Y and Z.
Ooh, that is frightening. Oh wait, they've shown Z though.
They've shown Z.
So what's
that
Z?
That makes me feel that like Class X is something.
Oh my
different.
Gosh, it's like I'm actually feeling scared.
So Class Z includes the Tholian homeworld, which I'm gonna Google for you guys.
Mm-hmm.
Don't worry.
Oh yeah, I also want to acknowledge a few things in the chat. Okay, so I like this comment from Missing Music who says, "Why does it look like the planet was just yeeted toward the sun?" And I agree with that, and I have a piggyback for that. I think this planet right here really looks like a marshmallow that like you're toasting over a fire, and then it just starts to erupt into flames. You see those blue flames? That's what it reminds me of. And then we've also got, I would love to be on Planet X, Think of the Tan, from Jan McCarthy, 1975. Then we've got Chemical X from the Powerpuff Girls, Missing Music. Yeah, X is just X and Z, very scary letters. I think that's why they used them here.
Okay, so
yeah.
Okay, so I looked up what the Tholians were, and there's a one-sentence description of what their race is, and if you look up a picture of Tholian spelled THOLIAN, they look pretty ridiculous, but that's just the animation quality they had back then.
So what's
the one-sentence description they have for the Tholians is this. The Tholians were an extremely xenophobic, non-humanoid, hermaphroditic species with a propensity for precision.
Okay. I think that sums it up well.
Yeah.
So, as you can see, we've ran out of letters. We've gotten to the end of the alphabet. So, we are done with this classification system, and we can move on to some qualities of habitable planets. So...
Holy crap.
So first, we have the Goldilocks Zone. And this, does one of you guys want to explain it? The Goldilocks Zone?
Jacob, you want to take it?
Sure. So basically, the Goldilocks Zone is the distance from the sun, in the case of the Earth, or the star that a planet orbits in the case of other planets, that it's a correct temperature range, so it's not too warm, and so that like life doesn't instantly fry, and it's not too cold, so it doesn't just like freeze and subject itself to hypothermia, or even just like collapse because its atoms are frozen and can't support themselves. I think that's what happens at absolute zero or something. Oh no, it'd be molecules that collapse, right?
Yeah, it wouldn't get to absolute zero, but you're right. It would get really cold, and some things that you don't want to freeze would freeze, like blood. Not a good thing to freeze, to have your blood
Maybe
freeze.
if there is one.
Yeah.
But basically, it's the correct temperature range that life can survive and not just like
Yeah.
die from temperature.
Yeah, and this is the reason for the name the Goldilocks Zone, is that if you get too close to a star, it's too hot, and if you get too far from a star, it's too cold. So for the sun, for example, if you have a bowl of porridge at zero point 0.1 AU from the sun, it'll be way too hot, it'll be scalding, it'll burn your mouth. And if you have a bowl of porridge 10 AU from the sun, then it will be freezing, it will be frozen, your porridge will be ruined. But if you have a bowl of porridge 1 AU away from the sun, then it will be just right. The perfect temperature for a nice bowl of porridge. And so that's what you get from the Goldilocks story. And that's why the name is like that. It's a little comical, I think.
Yeah.
Yeah. So
So should we move on to the...
the next topic. Okay. Magnetosphere.
So here we have a picture of Magneto.
Yep.
But we're talking about the Magnetosphere.
Mm-hmm.
And we have a pretty good diagram, so let's head over to the next slide real quick.
The Magnetosphere.
There he is again.
This man.
This man is everywhere.
Yeah. It's a great name, honestly. Magnetosphere. Just like, yeah. So the magnetosphere, all joking aside, is basically it's the Earth's magnetic field. It's generated in the Earth's molten iron like core, and basically the sloshing around of the viscous liquid iron basically generates this magnetic field and protects us from the sun's deadly rays. Yeah.
It protects us from solar flares.
Mm-hmm.
If Earth didn't have this, none of us would be here.
Yep.
Because we would all have been destroyed a long time ago
Mm-hmm.
by any number of like solar flares or anything else like that.
Mm-hmm. Yeah. Yeah, it's very important for life because the sun's radiation and many stars' radiation is what's known as ionizing radiation, and it's pretty much the ultraviolet light is what gives you a sunburn. And basically, it's the ultraviolet light, it hits your DNA and just shatters it, just tears it to pieces. I mean, your DNA is a very fragile, like, string, a very fragile little thread. And ultraviolet radiation comes in here, very high in energy, and just rips it up and, like, destroys your DNA. And so the reason that you get a sunburn, the reason that your skin turns red, is that a ton of your cells have been killed from this ultraviolet radiation destroying their DNA, and they have just gone through apoptosis because their DNA has been damaged. And so that's why it hurts, and that's why you get all red, because you just have...
Your cells are effectively committing mass suicide.
Yeah, because they basically get too screwed up to continue going on. And so, yeah, it gets very gory on the microscopic level. On the macroscopic level, all we see is, a little red and it hurts a little bit. But think of the cells, okay? Don't be greedy. You need to be conscious of how your cells feel. Yeah.
Come on, man.
So, yeah, come on. Be more considerate. So, yeah. So that's the need for a magnetosphere. If a planet doesn't have one, it's just like hands off, just we don't need you. Because another thing is that without a magnetosphere, you really can't have an atmosphere, or at least you can't have a permanent atmosphere, because what ultraviolet light does to your skin, it does equally, like, horrifically to a planet's atmosphere. It just shreds it off, tears it to shreds. All of the planet's gases just go out into space, never to be seen again. And you don't want that. If you are trying to terraform a place, and you put in a nice atmosphere, and then it just leaves in a few thousand years. It's just like, okay, what did I even do that for? It's very crucial. Yeah. So that's a quality of a habitable planet.
So yeah.
I'm going to go to the next slide. Oh.
Yeah, speaking of atmospheres.
Yes. Atmospheric content.
We have atmospheric content.
Yep. Yeah, basically, you can't just throw any gas down onto a planet's surface and expect things to just be dandy, because there are some pretty poisonous gases out there, and even the common gases, as you will see, can be deadly. So I'm going to go to the first one. And the first gas that you would want is oxygen. Now,
we all know him.
Yep.
He needs no introduction.
Yeah. I'm going to go right through. Oxygen. We all think of oxygen as a life-bringing atom, a life-bringing molecule. Just this great, great thing, glad to have it around. But actually, nobody knows the sinister side of oxygen.
Oh.
And oxygen.
I was thinking that.
Yep.
I was literally thinking that.
That's a reference.
That's an inside joke.
That's an inside joke. It's a video.
It's
on private now. It's a private video because things have gotten too contentious, but you do not know its sinister side. So yes, oxygen. Basically, if you've ever looked at a steel structure that has not been upkept well, you might notice that it's rust and like flaking, and it's gross. And that's because of oxygen. And so oxygen can do a similar thing to your body. It can rust you. You can become rusted. It's a theory of aging, is that basically over time, just damage from oxygen builds up in your body and you pretty much rust. And that's what causes you to age. And another oxygen, basically oxygen, if you have too much of it in your atmosphere, it's just not good. So here's what goes on. Say you had a 100% oxygen atmosphere, which is a very bad idea. While you inhaled it, it would instantly kill you. But say you had a 40% oxygen atmosphere instead of a 20%, right? 40% oxygen atmosphere is known to make people more upbeat and lively and stronger. And so people might think, oh, more oxygen is good. But it is not good, because if you were to continuously inhale a 40% oxygen atmosphere, you would age twice as fast because there's twice as much oxygen wearing you down. So you would have fun in the meantime, but it would slowly kill you, a lot like good food. It's great in the meantime, but it slowly kills you. And that's what oxygen does. And if you were to have a 40% oxygen atmosphere or 100%, the higher the oxygen content, the more likely wildfires are to just pop up and spread around the planet. We think California's bad right now, but if you were to have more oxygen in the atmosphere, you would just have a planetary-wide wildfire, which would just not be good. So oxygen is, you got to get it out of your mind. If this is what's in your mind, that oxygen is just wonderful. Because it's the right amount of oxygen is wonderful. 20 to 30%, 30%'s pushing it, but the dinosaurs were fine, so they're not fine anymore, but it wasn't because of oxygen. Yeah. So that's oxygen. Anything else to say on this topic?
Yeah, oxygen.
Yeah.
Might get a very good rap, but let me tell you, he's got a sinister side.
You know him by his Twitter.
Oh my gosh.
Oh my gosh. Yeah, oxygen. Yeah, I think that's good. We're going to go to the next one. We have nitrogen, or a substitute. So, you might be wondering, if I can't fill the atmosphere entirely with oxygen, then what can I even fill the rest of it up with? And that thing is nitrogen. For Earth, at least. 80% of Earth's atmosphere, a little less, 78%, is nitrogen. And the reason you want nitrogen in an atmosphere is because it's what's known as an inert gas. Now, we have to be a little careful with this. It is not a noble gas. A noble gas is specifically elements like helium, neon, argon in the periodic table, which we did last time, that do not react because they are single atoms and they have complete electron shells. But nitrogen is similar. It is an inert gas because although it has two atoms in this molecule, those atoms are bound so tightly together that it is very hard to get nitrogen to react. Not as hard as the noble gases, but like to a similar degree. Basically, nitrogen.
It's because N2 is triple bonded to itself.
Yeah, that's what I was about to say. Nitrogen is missing 3 electrons from a complete electron shell, and so it has the maximum bond that you can have because molecular geometry bars having a quadruple bond, but you can have a triple bond, and that is what nitrogen has, diatomic nitrogen. So it's very hard to break. When there's a fire, nitrogen does not burn. It just floats around, getting flung around by the air currents. But it's very hard to get nitrogen to burn. Some substances can do it in extreme chemistry, but that's not a problem for planets like this. So, but the thing is, right? What if your planet just does not have nitrogen? You might need to look for an alternative. So, you can look for alternatives, and an example would be argon. So we actually have argon in our atmosphere, but only about 1%. So it's kind of hard to find argon. Nitrogen, this is a big point. Nitrogen, oxygen, carbon, hydrogen, helium, these are all extremely common elements in the universe, and their extreme commonality allows them to be used en masse for things like atmospheres or oceans. So it would be hard to use argon because it's just unlikely that you would have enough of it, but argon's a possibility. And then another possibility is helium. And as I just said, helium is one of the most common elements in the universe, but the problem with helium is that it is way too light, which is what makes your voice high when you inhale helium. And why balloons float. This is actually a problem for us on Earth, is that we're running out of helium because every time you let off a balloon, it goes to the top of the atmosphere, pops, and then the helium gets stuck at the top of the atmosphere. But not only that, at the top of the atmosphere, solar energy, solar wind, solar flares, the stray radiation that makes it past the magnetosphere strips the helium off of our atmosphere along with the hydrogen. But we're not worried about hydrogen because it's locked up in so many compounds that we're not going to run out of hydrogen. All of Earth's oceans are just full of hydrogen. But helium does not make any bonds, so helium just leaves. But if you have a really strong magnetosphere or are really far from your sun, or you have any other terraforming option, you could use helium, except I'm pretty sure it strains your voice. But theoretically, life could evolve to be used to helium as a major component of the atmosphere. But yeah, so that's nitrogen or a substitute, basically inert gases. Do you have anything on this?
Nitrogen, way more alpha than oxygen. I gotta say, I have and in the periodic table, I think I mentioned this. On the periodic table, my favorite group of elements is the alkali metals, just because they spaz out in water.
Yeah,
but
that's always fun to watch.
And you should check out that stream, by the way.
Check out last week's stream.
One.
Three and a half hours, but watch some.
Yeah, 3.5 hours. Our guest there was Yui Films. You should also check out his channel. But nitrogen, definitely one of my favorite elements outside of the alkali metals. It's strong. It's independent. It can just triple bond to itself. That's definitely alpha.
Yeah, it's not needy.
And it makes up 78% of our atmosphere. So I gotta thank nitrogen for allowing me to make this stream.
Very well put.
That's
an
all I gotta
ode to
say.
nitrogen.
Thank you. I'm gonna write an ode to nitrogen.
I applaud you, except I'm snapping because it's poetry. Yeah. So so the next one, carbon dioxide. Or a substitute, but I didn't think to write or a substitute because I made this like at school during class.
Should we
not during
address
class,
chat?
Oh yes, there's a lot new in chat.
Yeah,
see.
we got a lot.
We got a lot. Where do
So,
we even start?
Let's start. I'll start off where. Oh, okay. So all the way back at the planet classifications, our friend who often appears in chat
Yes.
said that we should go to numbers now. Class 1 planet, Class 3, Class 7. I replied that Class 1 planets should have Taco Thursdays. Just an example of how bizarre number planets would be.
Yeah,
like,
totally
this is
crazy.
Clearly just like a fundamental aspect that
Yeah.
would be changed.
Yeah.
It goes on, and then they talk about ultraviolet light. And yes, that's correct. That's why your skin peels after a sunburn, because it is the dead skin cells after they have committed apoptosis, and they're all dead. So yeah, that's why it like hurts, because ultraviolet like does hurt, and without the magnetosphere, that would be all of us all the time. Or we actually wouldn't even be around to even experience the sunburn.
Yeah. We would still be single-celled organisms in the ocean. Before Earth had an ozone layer, and which is another topic that also
the sun was a death ray.
Yeah, the sun is a deadly laser, if you've seen that video. But yeah, basically life had to stay underwater and avoid the surface of water because it would just die if it went to the surface. And that's actually how the ability of sight first evolved, because a few bacteria mutated a light-sensing protein and learned whenever I sense light, I should swim downwards because it means I'm too close to the surface and I risk UV radiation. I mean, of course, they didn't know that. It's, their instinctual, coded whatever told them that, right? And, I mean, the rest is history, how the eye formed. I mean, if you've ever seen the Cosmos documentary series, I think they go on for 20 minutes about the evolution of the eye. It's such a wild ride, such a roller coaster of events. But that's where it all started, with a few bacteria not wanting to die. And yeah, that's where we get vision from.
So yeah, again, going further down in chat.
Yep.
Nitrogen is my guy, claims our friend. Amino acids are built on that, built on that stuff, and that's good. Very true, as we stated in our periodic table video. Nitrogen is one of the it's involved in organic chemistry. It's heavily involved in biology, along with carbon and oxygen and hydrogen. So yeah, nitrogen is definitely my guy as well.
Yeah.
He then said, what if we made nitrogen quadruple bonded? Well, and Mr. Music pointed out that yes, this is impossible. This is impossible because of the geometry of atoms as a whole and molecules. It's legitimately impossible to have a quadruple bond due to the lengths that would have to exist for the quadruple bond.
Yeah.
So yeah, that would be impossible.
Yeah, it's about hydrogen, or not hydrogen, about electron orbital reconfiguration and hybridization. Basically, the shapes that orbitals can make, you can get a tetrahedron, or you can get you can get different shapes, right? But there is no shape that puts all of the electrons on one side, because if you think about it, the electrons are all negative, so they're repelling each other. So they would never want to be on the same side. You can get 3 to be on the same side, and they aren't even really on the same side because of the way that the bonds work. It's kind of like a sideways bond. For 2 of the bonds in the triple bond are I think they call it a pi bond, whereas head-on-head bonds are sigma bonds. So you have 1 sigma bond and 2 pi bonds, which are these sideways bonds, right? And that's what allows you to have a triple bond. But the problem is the last electron is on the other side, and there's no way to have a bond that bonds with the opposite side, you know?
Yeah. I think chat has been properly
acknowledged, yeah. Okay, so carbon dioxide, greenhouse gases. These are important to an atmosphere. Now, this is kind of a reverse of oxygen, because everyone thinks oxygen is great, but if you have too much, it is actually not so great. Carbon dioxide and other greenhouse gases, everyone thinks they're horrible, but if you have too little, it's like really bad. You do need some carbon dioxide. It's like for Earth's like balance and homeostasis, you want a little under 300 parts per million. And of course, right now we're at like 400, so not good.
Yeah.
Straight up not having a good time. So, yeah, if Earth had no carbon dioxide, we would all freeze in a global snowball. Carbon dioxide is important for regulating climate.
It'd be a snow globe.
Yeah, snow globe.
Ah.
Yeah. Yeah. Carbon dioxide.
Anyways.
Carbon dioxide, it traps heat and that's important because otherwise you'd freeze. But if you trap too much heat, as we're facing that problem today, then you like don't want it as much. I mean, it's kind of simple, you know. You don't want to be too cold, too hot. Yeah. So, ozone. This is oxygen cubed. You've got 3 oxygens here instead of 2, which is interesting.
Jacob, do you want to say anything about any of this? I feel like we've been talking a lot.
Oh yeah. Do you have any insights?
I mean, other than that, they all got to be perfectly balanced, as all things should be. But
yep, they've got to be perfectly balanced.
Balance is the reason that a lot of the things exist, and that's going back to the Goldilocks Zone, how it's the perfect balance between being too close to the sun versus being too far from the sun. And we have like a pretty good balance of oxygen to carbon dioxide and nitrogen.
Yep.
All these things have to be balanced in order for life to like exist. And these are definitely the qualities of a habitable planet. So definitely, first and foremost, a habitable planet must have balance to exist.
Yeah, it's a very good theme here is that everything is good in moderation. Everything has a certain amount that is appropriate for it. And if you go over that amount or go under that amount, then you will not be doing well. So, yeah, so ozone, right? It's basically instead of 2 oxygens double bonding to each other, 3 oxygens bond and make these like 1.5 bonds, which are really weird. It's called like a resonance structure. And it pretty much just means that when you're in chemistry class and your teacher tells you to draw the Lewis structure for ozone, they're just trolling you because you have to draw 2. It's impossible to draw 1 Lewis structure that describes ozone. And yeah, it's just weird. How jovial, how jocular.
Jocular.
Yeah, basically.
Such a jest.
I jest. Ozone it's a little odd just in the way that it makes 1.5 bonds instead of 1 or 2. But, you know, that's chemistry. It's a lot simpler as these 3 spheroids next to each other, right? It's a lot easier to just picture it like that. So basically, ozone, along with our magnetosphere, ozone helps block out ultraviolet radiation from the sun, because when ultraviolet radiation hits ozone, I don't know, it starts vibrating or something. I'm not sure on that, but I know it just absorbs it and prevents it from getting to the ground. So you want ozone. There was a big scare, I forget which year it was. I mean, before our times. It was...
Where there was a hole in the ozone
Yeah,
layer?
It was the chlorofluorocarbons from like refrigerators and aerosols were all being released into the air. And chlorofluorocarbons chemically react with ozone to destroy it and just turn it into like normal oxygen. And that was not good. Very not good. I think there's still like a hole over Antarctica where there's just like you're gonna get like more radiation there, and you need to put on more sunblock
Yeah.
there. But you know, it's fine. Like only like 1,000 people live there, so we're good.
So we're good.
The penguins are not good though. It's they
Just
they get
smile and
sunburns.
wave, boys.
Just smile and wave. Anyway, so yeah, ozone's important. Ozone and magnetospheres are basically your big defense mechanisms against the sun, because again, about moderation, the sun is good in moderation, but too much sun is not good. You don't want all of the unfiltered rays of the sun to come at you. You just want like visible lights, and that's it. So yeah, so those are all your materials that you would want in a atmosphere.
So
Now
now,
we have-
let's get down into the down and dirty.
The down and dirty.
Literally.
Yes. You've got soil composition. So these, I pretty much based them on the biogeochemical cycles, which is a real mouthful, and I really like saying that word from biology class last year. The biogeochemical
yeah, I remember.
cycles.
We had to draw out all of these cycles.
Yes, we had to draw out all of these cycles. It's basically the materials in the Earth's ground. They get swept away in runoff and like rain and stuff, and they go out into the ocean. And then they like build up sediments on the ocean floor, and then as plate tectonics occur, they come back up to the surface. They go in the atmosphere. It's just a wild ride. There's like fluxes and stuff. It's just all in motion. But basically, these are things you need to have in your soil, and the biogeochemical cycles are important, and important not to disrupt, because we want to make sure that our soil does not get drained of these substances, and so these are the substances. Not all of them, of course, because some of them I've like I didn't include all of the cycles. These are because some of them are like, I don't know, like the water cycle. Like we say later that you need water or another alternative, but you know. So the first one is the nitrogen cycle. So, nitrogen, you might think, why would you need nitrogen in the soil? You have it in the air. Well, the thing is, plants need nitrogen, and they cannot take it from the air because nitrogen in the air, as we said, is triple bonded. And while that triple bond is good because it means that it is inert and it won't react, it is also bad because it is inert and it won't react. So if a plant wants nitrogen, it cannot get it from the air. There are some bacteria that are able to rip apart the nitrogen bonds, but it takes a lot of energy. It's a lot simpler to just find in the ground. You have some of these ions here. You've got the ammonium ion in the middle. You've got to the left the nitrite ion, and to the right the nitrate ion. The naming system's pretty good actually on this. This is one area where science was made good naming systems. It's all about the number of oxygens you have. It's really strange, but once you learn it, it's good. So this is where the plants get nitrogen, and you basically just need nitrogen in the soil. So yeah. This is actually a big problem with terraforming Mars, is that Mars has a severe nitrogen problem. There's just a total shortage of nitrogen there. You would not have enough nitrogen to wastefully fill up your air. You would not have enough for the soil and for the plants. So Mars has an issue. But you could just collect some nitrogen from Venus and send it to Mars, because along with every other atmospheric component, Venus just has a lot of air and stuff. A lot of material, so it could donate. You could have a nitrogen transplant from Venus to Mars, but it would take a lot of cargo spaceships and a lot of rocket fuel. So, yeah.
Mm-hmm.
Do you have anything on these, on nitrogen?
I gotta tell you, nitrogen, I love it. Stated this before. Love it. Great. Awesome.
He's
helps
your guy.
You, helps your plants.
Yep.
Helps everyone. Helps your neighbor. Helps your landlord. Helps everyone. It's great. Nitrogen.
Yep.
The cycle. Awesome.
Yeah.
Beautiful. Creates our big blue planet.
Mm-hmm.
We wouldn't be here without it. So I'd like to give a shout out to nitrogen.
Shout out to nitrogen. Yeah, they use nitrogen in fertilizers because when a soil when an area of soil is depleted of nitrogen, it just cannot grow anything anymore.
And that's another thing.
So.
Fertilizers, when it rains, the fertilizers can be caught up in the runoff, and they can go into ponds actually, and then the nitrogen actually like accelerates the rate of growth with the algae in the pond. So then the algae ends up like covering the entire pond and actually suffocates the pond per se, because it stops sunlight from getting into the pond, so everything dies below the water. So I just want to call out nitrogen on this one.
Yeah,
come on, man, what are you doing?
Yeah, and if you didn't get that, I'll put this in Minecraft terms. Imagine you are bone mealing a sapling, right? But then you accidentally bone meal the pond, and then all the algae grows, and you did not want it to grow. And they're pretty much like weeds, just unnecessary, and then they kill everything else. Be careful with the bone meal. Be careful with your nitrogen. You have to use it appropriately.
He's a powerful ally, but he can be a dangerous arch nemesis.
Yes, please use nitrogen responsibly.
Use it wisely.
Use it wisely.
Yep.
So that's nitrogen.
You gotta use it wisely.
Yeah. So I'll go to the next slide. We have phosphorus. Phosphorus is nitrogen's older brother, right? Nitrogen's older brother. It is right under it on the periodic table. It's just a more massive version of nitrogen, and it's fairly chemically similar, except it has some interesting properties. So what do you have to say about phosphorus?
Phosphorus. Phosphorus. You might know him as good old P. He's number 15.
Yep.
On the periodic table. We covered him in our earlier stream. And his cycle, this was like the one that I didn't really do a lot of work on. We had a group project on this. But from like what I remember, phosphorus was like mainly found in like crystals and such, and then those crystals were like mined by humans, and then phosphorus got used in like fertilizers again. I think
it's another additive for fertilizers.
In other things, and then that ran off to the ocean, and then it sank back down into the rocks, which were then mined again. So that's just what I remember from our like work on the cycle. But phosphorus itself, it actually works with calcium to help build your bones, so remember to drink your milk. So you can find phosphorus in like a lot of things, like meat, poultry, fish, nuts, beans, and like dairy products. Too high, I'm pretty sure too high bad for you.
Too high phosphorus levels.
But
So this is really interesting. Phosphorus. So phosphorus and sulfur, which we'll go to next, they have really interesting properties, because nitrogen is 3 away from getting a complete electron shell. So it wants to gain 3 electrons. Phosphorus is in that exact same position. It's 3 away. So you would think it would want to gain 3 electrons. And oftentimes it does. But sometimes phosphorus just, I don't know what he's doing, man. He just goes backwards and loses 5 electrons and says, I'm getting rid of these electrons and I will make 5 bonds. That is what phosphorus does sometimes. It is just perplexing. Sulfur does the same thing, but it's even worse, because how oxygen is 2 away from a complete shell, sulfur is also 2 away, but it's 6 away from emptying the shell. And sometimes it just goes like haphazard, like throws caution to the wind and says, I'm going to get rid of those 6 electrons and make 6 bonds, which is just crazy to think about. So if we look at this phosphorus ion here in the center, this is I think it's like hydrophosphate, something like that, where basically both of the oxygens that have a hydrogen attached are taking 1 electron away from the phosphorus, so that's 2 electrons taken. Then the like negatively charged oxygen is also taking one, so that's 3 electrons taken, and then the oxygen off to the side with no hydrogen is taking another 2 electrons, so that's 5 electrons, and phosphorus now has an empty shell, and this is an ion. So phosphorus, it's bound up in these compounds. To the left, we have iron 3 phosphide, which is like a compound. I forgot what the right was supposed to represent, but it's another transition metal with phosphorus. So phosphorus can gain electrons and it can lose electrons, which is what I'm trying to illustrate here. Because on the left with the iron 3 phosphide, iron is donating 3 electrons to phosphorus, and phosphorus is completing its shell. So, that's good. But in the middle, it's just kind of going crazy, and it's a little unexpected that it would go this way. But that is why phosphorus is so important in biochemistry, because it can make these 5 bonds. It can really connect all these different elements, and that is why it is like used in the body so heavily. It's used in your DNA. It's also used for adenosine triphosphate, which is your cell's batteries. So the phosphorus cycle is very important, and it's very important that you have phosphorus in your soil to be a habitable world. Any more on phosphorus?
So, no, I'm actually ready to head over to sulfur.
All right.
I got something to say about sulfur.
Sulfur, yes.
So sulfur is, of course, most known for its terrible smell.
Mm-hmm.
It's usually described as that of rotting eggs.
Mm-hmm.
And if you go over to like the Wikipedia on sulfur, it literally has a category describing its odor.
Oof, that's rough.
So sulfur spelled with an F if you're from America, and spelled with a PH if you want to be wrong.
No, okay, I have to address that. I use
that was a joke.
Okay, this is the scientific community's agreement. Basically, it's with a pH, and this is similar to the aluminium controversy. I choose aluminium and sulfur with a pH, and it's proper. And this is the thing.
Deviant.
This is the thing, okay? American English. Oh, what were you saying?
What did you say, Jacob?
That's just because these other countries speak English traditional and we speak English simplified.
Basically, this is a really interesting thing. So American English, there were like American adverts, like advertisements when the printing press and stuff was around. It was charged by the letter. So a lot of American words compared to British words are just like missing a few letters, and you're like, why is that? Like, why is it missing all these letters? And that's just because they were like, we want to have a cheaper advert, so we're just going to get rid of all these letters. So sulfur with a pH, they're like, that's inefficient. We can just change it to an F. Aluminium, we can just get rid of that I. This happened for the word color, or color with the U. Armor, I mean, it's all pronounced the same. Armor, all those words that end in OR for Americans and OUR for British people. And I'm not sure how they spell donut in British. In Britain, I think they changed this just like all around because it was such a terrible word, but they spelled it DOUGH, nut. So as in dough. And they just got rid of those 3 letters and made it D-O, nut. So, yeah. But it's proper to use sulfur and aluminium. And as I said last time, if you want your scientific papers to be easier to find, then you should use the pH and the IU, because when people control F and search for a paper on sulfur, they are more likely to search for a paper on sulfur pH instead of sulfur F. So yeah, that's kind of what I do.
Yeah. So how the sulfur cycle basically works is that it's got like 4 main steps, you could say.
Mm-hmm.
So sulfur gets like mineralized. Like organic sulfur gets mineralized into inorganic forms such as hydrogen sulfide, which is just H2S.
And it's the molecule on the left here.
Yes. So yeah, that's that on the left. Then there's oxidation of that hydrogen sulfide.
Mhm.
And then there's reduction of that sulfate to sulfide. And then there's the incorporation of sulfide into organic compounds.
Now that's really interesting because the three molecules I chose really illustrate that. So,
Yeah.
as you said, the oxidation of sulfur. For all those people that aren't taking chemistry, oxidation is the release of electrons, the loss of electrons. And as you see in this central ion here, this is a sulfate ion. And basically, each of the oxygens is taking two away from the sulfur, and this oxygen has a -2 charge. So sulfur is losing 6 electrons, which is, as I said, surprising because you would think it would want to just gain 2. So this is oxidized sulfur, lost a ton of its electrons. And then the next step, as you see, the sulfur has a negative charge, which means that this is sulfide and it has completed its electron shell. So some interesting stuff.
Yeah. So yeah, the chemical formula of sulfate is just SO4.
Yep, SO4,
like
2 minus.
Yeah, and -2 is the charge.
Mm-hmm.
So some general uses of sulfur, like I said, for its terrible smell.
Yeah.
Sulfur is used actually in the production of like rubber. Weirdly enough, it's used as a fungicide.
Okay.
And by the name, you can tell it's something used to kill like funguses or fungi. Rather.
Yeah. Funguses.
And it's also used in gunpowder, which is why you'll see gunpowder or you'll hear about gunpowder just being described as like this kind of intoxicating, like disgusting smell. And like, or if you've like experienced gunpowder like firsthand, it does not smell that good.
Yeah.
Obviously it's used in sulfuric acid. And that is quite an important acid used in a lot of experiments and just a lot of industries.
Yeah.
So, pyrite, and this is just going into kind of like my interest, but pyrite is a shiny yellow mineral. It's actually how it pretty much got to Earth. How it's most commonly found is that it comes down from asteroids.
Oh, interesting.
It's also known as fool's gold.
Yes, I wanted to mention that fool's gold.
Yeah, it's fool's gold. If you look up images of, definitely one of my favorite minerals, and it consists of iron disulfide.
Huh. Iron disulfide. That's interesting.
Yeah.
That's cool. So that's sulfur.
So yeah, that's
you need sulfur in your soil. Anything else on these 3 biogeochemical cycles?
These 3 biogeochemical are essential, and like Jacob pointed out earlier, it's the balance. Like we said, if one of these kind of gets out of whack, and most notably they get out of whack due to human interference, like we said, if nitrogen goes out of whack and fertilizers run off into lakes, those lakes will start dying, ecosystems getting destroyed by it. So even though most people just, it's just dirt, like it's just what's in the dirt, like most people wouldn't care about this, but it's actually like the effects of it are exponential to ecosystems around the Earth. That's a lot of ease.
Yeah.
But
dirt. I think like there are whole like fields of study. I mean, not actual fields, but like people go into studying like the ground and ecosystems and like the chemistry of soil. It's like really interesting. It's not just dirt. Although it is just dirt, but it's like, science is everywhere,
So let's head over to the next, which is
the
The
need
need for a
for a solvent. Yes, the need for a solvent. This is a very interesting one. A solvent is basically a polar or ionic like material, a polar like substance that if you put ions in it, it breaks apart those ions, it dissolves them, which is hence the name solvent, dissolve. That is what water does, say, when you put salt in water. The salt dissolves into the water because water is an example of a solvent. And you also have some other solvents around that we're going to look at in a little bit. But basically, solvents are important to life because of their polarity, as I said. It's very important for chemical reactions and osmosis and diffusion. In biology last year, I had a lot of talk about osmosis and diffusion, but basically, water is used to transport materials in and out of cells because of the osmotic process or whatever. It's like really weird, but it's basically if water has a lot of stuff dissolved into it, like important stuff, like for your cells, then it'll go into your cell. Like the water will carry it into your cell. It's kind of complicated, but it's just important, you know.
Yeah.
I mean,
Jacob, do you have a
Oh, yeah.
favorite element in the periodic table? I was just wondering.
I'd say I do. I don't know the periodic table that well, though.
Well, if you don't, then there's a great stream.
There's a great live stream for you.
Max, do you have a favorite? Do you have a favorite element?
Yeah, a favorite element. Let me think. There's just so many. 118. Let's see. I really, that's a hard one because I feel like they're all so important. I guess if I would have to pick a favorite, it would probably be. I think I'm gonna have to go with uranium, and that's because of its nuclear properties. Very interesting. I have a penchant for the nuclear. Me and Brendan, as we said, we were gonna build. We were gonna build.
That sounds like a band name.
A penchant for the nuclear. Yes. Yeah. So, yeah, I find it interesting. It's interesting form of energy, but yeah. So I like uranium. Yeah. So should we get into some of these?
Let's go on.
Okay. So
talk about
properties
of a good solvent.
So a solvent, it has to. It doesn't like to be a good solvent. It should be polar. It should be liquid, and it should be very common in the universe, so that you have more than like a gram of it on your entire planet. And so, quickly, I think we should just explain polarity. Do you want to explain it?
Yeah, sure.
Okay.
So polarity, most common. Water is
the most common polar.
Water is polar.
Yeah.
So it means that there's a constant flow of like positive like to negative. Because in a H2O atom or an H2O molecule, I should say.
Yeah.
The hydrogen
a formula unit
is charged positively, and the oxygen negative.
And these are partial charges.
Polar. Yeah. It makes it like it makes it polar, and what that means is that it allows for an electromagnetic charge to pass through it pretty easily, which is why like water is like dangerous when there's like power lines down, or when like when they tell you to get out of a lake because there's a storm. It's because even if you don't get hit by lightning, but you're in the water near where lightning strikes, you can still get electrocuted because the electromagnetic force can pass through water and like spread outwards.
Yeah, it's really
So
interesting.
yeah,
It's like the electrolytes dissolved in water. So this is like your minerals, your like some potassium, sodium. Those dissolved materials that are in all water, at least in trace amounts, are what give water its conductive properties. And water can only dissolve these materials because it is polar. So that's like yeah, as you said, why you should not be in water during a lightning storm unless you have absolute assurance that it's like 100% like water with nothing dissolved in it, which is pretty much impossible to get. Um, but yeah, so really polarity, it stems from electronegativity on the periodic
yeah.
table. I made a video about electronegativity a while back, so you could watch it later, I guess. But basically, electronegativity is that oxygen is two away from completing an electron shell, whereas hydrogen is it's one away from completing a shell, but also one away from emptying it. So it can go either way. It doesn't care as much. But oxygen is not going to give up electrons. So oxygen kind of hoards the electrons in the water molecule. So that's what polarity is, and uh, all of these, all of these except one are polar molecules, and the one that isn't a polar molecule does have polar bonds, which is basically
Yep.
the bonds are polar, but because of the shape, it isn't strictly polar. So we'll get into that. So first, we have dihydrogen monoxide, a very typical substance with a scary name. Water's scientific name is frightening, and I was able to use it, me and Brendan, when we worked, or not worked, but like we were with our middle school's TV broadcasting program. We made like videos for it, and we made this fake comedy video about it was a PSA about the dangers of dihydrogen monoxide, and we were like, it's very dangerous. You should not drink dihydrogen monoxide. Studies have shown that there is dihydrogen monoxide in the school's water, and a lot of people just did not realize because they like scientific literacy. They just didn't have a lot of that, so they didn't know that dihydrogen monoxide was water. So yeah, really, it's been a ton of pranks like over time. It's a classic April Fool's Day newspaper publishing articles about dihydrogen monoxide. It's basically a lesson that scientific literacy is a very important thing, and you should try and be scientifically literate. Otherwise, you'll get hoodwinked by dihydrogen monoxide pranks. So yeah, I mean, water, you know what water is, right? Everyone knows what water is.
Yeah.
Yeah.
I'm pretty sure all of our viewers know what water is.
Yeah. Yeah. Basically, another thing about water is that since it is polar, it expands when it freezes, unlike most substances that contract. And that is pretty important for a lot of these solvents because basically you want it to float to the top of a lake. If a lake starts freezing over and it starts freezing from the bottom, then everything's going to die. But if it starts freezing from the top, then you can kind of preserve things underneath. Yeah, so that's water. I'm going to go to the next one, the next slide. I mean, I don't have much to say about water.
Water?
Yeah.
I'm a fan.
You're a fan of water?
Next.
Okay. So our next solvent is ammonia, which...
Ammonia's chemical formula is NH3.
Yep. As you can see,
which you
3
can see
H's and
in
an
the back.
N. Yeah.
Again, this is polar, right?
Yeah, this is polar. It is slightly less polar than water, and the reason is nitrogen is a little less electronegative than oxygen is, and the hydrogens here are spaced out a little more, so it's a little less polar, but it is still fairly polar. Ammonia is, I think, isn't it what gives urine its urine smell?
Yeah,
is
it's
ammonia.
pungent smell. Yes,
Yeah.
that is
Uh,
what ammonia is known for.
Yeah.
Also, if you combine ammonia and bleach, that is the recipe for mustard gas.
Yeah. Oh gosh. We do not endorse
We do
the
not.
combination.
Gravity Max does not endorse.
Gravity Max does not
creation or
endorse.
production of mustard gas.
Yeah. Do not. Oh my gosh. Could you imagine someone just being like, "Oh, that sounds like an interesting science experiment." Please do not mix ammonia and bleach. Please, I beg of you, don't do it. It won't turn out well. Anyways, so ammonia is interesting. So it's polar, it's a solvent, it's a little less polar, and the thing is, it has a different liquid state than water. So water is liquid from 0 Celsius to 100 Celsius at like atmospheric pressure, whereas ammonia is like gaseous at room temperature, and its range is about negative 78 degrees to negative 33 degrees Celsius. So that's when it's a liquid. So this ammonia, you could use it more for like the outer planets. So the moons of the gas giants may use ammonia as their solvents if they had life, because they're colder. So ammonia would be a liquid there. And yeah, ammonia, it's pretty interesting. It's all of these solvents are basically in this one family of molecules, which are basically some element and as many hydrogens as they'll take. Oxygen will take 2 hydrogens, nitrogen will take 3. So they're very similar. They are very chemically similar compounds.
Yeah, an interesting thing to do is with any of these, you can look up like ammonia-based planet.
Mm-hmm.
Like you can obviously look up water-based planet, but come on, man.
Yeah.
But when you look up ammonia-based planet,
mm-hmm.
It has like literal like oceans full of ammonia,
mm-hmm.
and it has a dark brown, a dark brown hue because of the alkaline earth metals that are dissolved in ammonia.
I would not like that if I lived on that planet.
So
you've got the faint blue orb. What do they call it? That one picture from Voyager, the pale blue dots.
Oh,
you've got
pale blue dot.
Yeah, you would have the disgusting brown sludge. That's your planet.
So there are an estimated 24 billion ammonia planets in our galaxy, in just our galaxy alone.
Wow.
It's more than half as abundant as methane planets, which we'll get to.
Yep, that's the next slide.
And they make up 4.6% of all 524 billion terrestrial planets and 2.9% of all 820 billion planets in our galaxy.
Yeah, so that's really
very interesting.
Yeah, so it's really common. Obviously we have a Earth-centric mindset, Terra-centric mindset, because we live here, and we have never gone anywhere else other than the moon. So these are kind of foreign concepts, but you really don't think of ammonia as the bad-smelling gas that causes mustard gas with bleach. You need to think of it in this context as a liquid that could possibly harbor life, because at colder temperatures. And it's interesting, actually. The reason that ammonia has a colder liquid temperature range is because it is less polar than water. A substance's polarity means that it can make hydrogen bonds and dipole-dipole bonds, which are basically these weak intermolecular forces that kind of keep it together. And since water is more polar, it's very polar, it's able to stay together longer and at higher temperatures, whereas ammonia is weaker with its polarity, weaker with its dipole-dipole bonds, and it boils off at a lower temperature. So, next slide. Methane.
Methane, like I said, almost twice as abundant, like methane-based planets are almost twice as abundant as ammonia-based planets, and you can even see it on such as Titan.
Yeah, Titan.
Saturn's moon.
Yeah. this is really interesting, actually,
Yeah.
because methane has carbon as its central atom, whereas nitrogen is ammonia's central atom. And if you look at the commonality of these two substances, it's really related to their commonality in the universe. Carbon is more common in the universe than nitrogen is. So since carbon is more like abundant than nitrogen, it makes more compounds, and you end up with more methane-based planets. Even though methane really isn't as good as a solvent, but
Yeah.
So,
And what's the reason for that?
okay, yeah. So this is basically methane has a bit of a problem. Methane is polar in its bonds, but it is not a polar molecule, and the reason is look at its shape. It is tetrahedral. So
look at this man's shape.
Look at this
Look at
shape.
him.
This is a tetrahedral molecule, which is not good for polarity because basically each hydrogen has a slightly positive charge and the carbon has a slightly negative charge. And you might think, well, that's just like ammonia and water. That's like nothing new here. But the hydrogens are equally dispersed around the surface of the carbon. So you have a molecule that is slightly positive on every end. It's like a magnet that only has north ends, so it just repels all other magnets. It's interesting. So it's kind of a solvent, but it isn't the best, you know. It's theoretically, it could be used for life, and as you see, it's more common than ammonia, but it's really subpar. So methane's liquid state is negative 182 Celsius to negative 161.5 degrees Celsius, which is very cold and very slim for a liquid range. And the reason for that is that, as I said, it's all positive charges on the outside. Imagine if you were trying to keep a substance together and it was all made of north end magnets, right? I mean, it would be hard to keep that together. So that's
Quite.
methane's problem. And it is just fairly weak in its polarity in general, even if it didn't have the symmetrical problem. Carbon has an electronegativity of 2.5. Nitrogen is 3.0, and and oxygen is 3.5. Hydrogen is 2.1. So methane is only a bit more polar a bit more electronegative than hydrogen. So it's just not very strong, you know.
It's terrible, trash solvent. We're gonna put all of these solvents on a tier list.
Yeah, we put them on. Yeah.
And let me just give you a peek behind the curtain. Methane does not do well.
Yeah. But we shouldn't be too harsh on methane. It's hard to be a solvent in general. I mean, could you imagine a planet based on, I don't know, sodium and hydrogen molecule? That would not go well.
Ridiculous.
Yeah. So methane.
That would probably be a Class Y planet.
Class Y. Yeah. Methane, it's sad. It's kind of like the run of the litter, but it does have more planets than ammonia, so, you know, it gets its heyday. It's, you know, so, do you have a comment on methane?
No, I was just yawning.
Oh, okay. All right, so I'll go to the next one. We've got hydrogen
fluoride. So earlier we mentioned activity. Fluorine is the most electronegative element.
Yes, it is the most electronegative. Its electronegativity is 4.0.
Yes.
So, yeah, hydrogen fluoride, when dissolved in water, is known as hydrofluoric acid, and it is not fun, but that's its aqueous form. Hydrogen fluoride alone could be a solvent, but it's complicated. So hydrogen fluoride is more polar than water, whereas ammonia was less polar than water because you only have one hydrogen here because fluorine only wants to make one bond, and since fluorine is the most electronegative element, it just pretty much steals that hydrogen's electron. And yeah, so its liquid state because it has more polarity, it is able to have a higher liquid state than some of these other molecules, and that liquid state is negative 83.6 degrees Celsius to 19.5 degrees Celsius, which is a really wide liquid range. That is pretty good if you think about it, because I think that's slightly more than 100 degrees of range. So I think it's like 103 degrees of range, whereas water only has 100 degrees of range. So you can see that this is a very polar substance. It's even ionic, honestly. It is considered ionic.
Its only downfall is that its boiling point is 19.5 degrees Celsius or 67 degrees Fahrenheit.
Mm-hmm.
Why I said 17.
Yeah.
67 degrees Fahrenheit. So if this was to exist on a planet, that planet would always have to be under 67 degrees Fahrenheit.
Well, not always. I mean, we have water. We have gaseous water here. It would have to be.
Yeah, that's true.
It would have to be a few notches colder. I do acknowledge that. It would have to be a little colder. But not as cold as ammonia or methane planets.
Yeah. Yeah. It's also like commonly found as like hydrofluoric acid, which is bad.
Yeah, it's pretty bad. But
Gravity Max does not
condone
the consumption of hydrofluoric acid.
Yeah, just honestly don't. So hydrogen fluoride, when mixed with water, is a pretty deadly acid. But if you think about it, if you have a hydrogen fluoride world, there would not be a lot of water there, so might not be as much of a problem. And if you have a hydrogen fluoride world that life exists on, that life would be specifically evolved to deal with the hydrogen fluoride and its negative side effects.
Should we move hydrogen fluoride up the tier list?
Yeah, quickly move it up the tier list. Just put it.
Okay, I'm throwing it on A.
Really? Put it with ammonia.
Sound pretty good. Actually, no, I'm gonna B.
Yeah.
Only because of the acid part of it.
Yeah. Okay.
Before we had thrown it on D because our gut reaction was that.
Yeah.
Come on.
We had a visceral.
It's acid, but Max does make a good point. There wouldn't be water. There wouldn't be a need for water on a hydrogen fluoride planet. Now, it's not saying that water wouldn't form.
Yeah.
But
it would be less common.
Less common.
Yeah.
So spoiler, it's on B.
Yeah,
right now.
so that's hydrogen fluoride. It's a pretty interesting one out of all of these. Next, we have hydrogen sulfide with a pH, as always, as customary. So this is actually the most chemically similar to water because you have a oxygen group element and two hydrogens, chalcogen or whatever the oxygen group was called, and two hydrogens.
Yep.
Yeah, so it's pretty similar to just standard water, but it has a few issues, a few underlining issues, and here they are. So there's a big drop-off in electronegativity as you move down the periodic table for the P group elements, and that is oxygen is 3.5, sulfur is 2.5. This is partially responsible for sulfur's tendency to go backwards sometimes and just empty its shell, because with the 2.5 electronegativity, it's like not as repulsive. It's like if you tried to broach the idea to oxygen of emptying its electron shell instead of filling it, oxygen would laugh you off. It would be like, you're ridiculous, get out of here with that insane offer. But sulfur is more willing to do that. So hydrogen sulfide is not as polar as standard water, but it is still a solvent because it's still polar. It's still got the asymmetry that you need for a polar molecule. And its liquid range is skinny and low. It is negative 82 degrees to negative 60 degrees Celsius. So it's not the best. It's
not the best.
Yeah. So here we go. I'm going to go to the next slide, and this is just some stats so that you can picture this. Okay. This is percent ionic character, and this is a measure of 0% is a pure covalent bond, 50% is like the maximum polar bond, and 100% is pure ionic bond. I don't think you can actually have 100%. You can get very close, but the way that it's formulated mathematically means that you really cannot have 100% ionic character because there's like exponential and limits and stuff. But just for these purposes, we can see water has a percent ionic character of 39%, as it is the red bar for oxygen's red CPK coloring. Nitrogen, ammonia is 18%. Ammonium is the ion, remember, NH4 from a while back? You can see where that name comes from now. But ammonia is 18%. Methane is 4%. Hydrogen fluoride is pretty garbage. Hydrogen fluoride is 60%, and sulfur hydrogen sulfide is 4%. So, this kind of helps you picture it. So, the next part is the liquid range all together. Our line here is the 0 degrees Celsius marker, and we can see that hydrogen fluoride has a wide liquid range, just like water. Ammonia has a pretty standard, pretty wide liquid range, and methane and hydrogen sulfide are just,
they're just sucking this.
They're pretty
episode,
bad.
Man.
But the only redeeming trait of methane is that it is much colder than the others. It has a much colder liquid range. So if anything is colder than like negative 100 degrees Celsius, it's just kind of gotta use methane. It's like, you're pretty much the worst one here, but we gotta use you just because what else do we have? It's like, yeah. So I will go to the tier list now.
Okay, here's our tier list. S. At S is the classic dihydrogen monoxide.
Yep.
Good old water.
Yeah, it's the only one that has confirmed life, so of course it has to be S. It's the only molecule that we know of that can support life as a solvent. So there it goes.
So at B, we have both ammonia and hydrogen fluoride, mostly due to their polarity, how common they are,
their temperature ranges.
The only reason, and their temperature radius. The only reason that hydrogen fluoride isn't up due to its like bueno polarity is because it has a pretty low boiling point.
Yeah. Well, no, that's fine. That's fine though. The boiling point's fine. It's the fact that it's a little too polar, a little acidic from its polarity.
Yeah, exactly. That's my second point. It's most commonly found as hydrofluoric acid.
Yeah. I would actually argue...
I just don't like that it has a high boiling because I hate cold temperatures.
Oh, okay.
I can't stand them. So if I was forced to live on hydrogen fluoride world, I wouldn't be having a good time. A, both because I would die, but B, because it would be cold.
Well, yeah, but the thing is, if you think about it, hydrogen fluoride-based life would find negative 10 Celsius rather toasty.
Rather toasty.
So, yeah, hydrogen fluoride, it's a bit too polar. That's its downfall. That's why it doesn't get the A tier. Ammonia has an opposite issue. Its temperature range is a little skinny. It's a little subpar. I mean, it's not as bad as hydrogen sulfide or methane, but it's not the best. You could do better ammonia. But it's got a nice polarity, so that's why ammonia's B tier. And then we get to hydrogen sulfide, most chemically similar to water, but it's just like a worse form of water.
In its sulfur's footsteps and just stinking it up.
Yeah, it's D tier.
D.
Yeah. If you think about it, it's just a worse version of water. Skinny temperature range, barely even counts as polar. It sucks.
Yeah. I would like to address the chat real quick.
Oh, yes, the chat.
I know we've missed like half of the chat that's been going on because we've been getting into this, but I just want to respond to one comment real quick. From Missing Music, Cold Good, after she has stated, I love the cold. I just want to point out that being too cold versus being too hot. Being too cold has killed literally billions more of organisms than being too hot. Being cold stops productivity. Being cold makes me feel bad. Being cold sucks. Thank you.
You know what?
That's
Maybe
my
we can have
scientific
missing
analogy.
music on in the future to debate the coldness.
Yeah.
The benefits. I'll be the
That
moderator.
is a debate I have already won because we can look at history, man.
Uh-huh.
Being cold, and again, cold isn't even a real thing. It's lack. Imagine not even being your own thing.
Yeah,
Way
it's
to
lack
go,
of heat.
cold.
Yeah. Yeah,
Jacob,
these
what
are
do you
interesting.
think about this? What do you think about hot versus?
Well, let's see. Oh.
Well, I want to hear what Jacob.
Oh yeah,
thinks.
yeah. Sorry.
I think that prefer too much heat to too much cold.
Exactly.
Because too much cold is miserable. At least like too much heat's an energetic kind of pain.
Exactly.
I don't
Cold
know.
is just depressing.
I gotta
Exactly.
say, I
He's
gotta
got
say,
it right.
I'm gonna take a controversial move here. I like the cold better, but not.
I
I
want
don't-
to address chat again.
Okay.
I know we're going off topic.
Okay, I don't like either, but it's just kind of like cold is like cozy, you know? Like you just don't have to go outside, you just get a nice blanket, sit
Listen,
by the
Max,
fire.
you're on the verge of starting a war. You do not want to fight.
Okay. I'll stay out of it though, but
Okay, I will not address chat again because.
but no, okay. I do agree that cold is fairly miserable. Occasional cold is nice, I gotta say. I like contained cold. I like artificial cold.
I'm not blind to the fact that black would not exist without white, and that good would not exist without bad.
Yeah, I do agree that the places I have lived in the north and the south, and I agree that the north, the winter is miserable. It is freezing cold. It is horrible. And if you just want to go outside and like go to your car, then you just like freeze.
You
and
know
you
how
need a jacket.
cold it is outside right now?
How
you
cold
take
is
a
it?
Guess?
Let me guess.
Outside temp.
50 degrees Fahrenheit.
Nah, it's 40 degrees.
Oof.
That's insane. You hear
that
me?
sucks.
And on Friday, this very Friday,
Mhm.
the low,
Yeah.
26 degrees.
Ooh.
26 degrees.
That
It's
sucks.
just the fall.
That's really
It ain't
sad.
even winter yet.
Yeah.
That's
This morning,
feel
I went
bad
out
for
to
you
get the
guys.
mail, and my life flashed before my eyes.
yeah. Yeah,
thought
I
it was
know that
it.
feeling.
I thought I was about to either turn into Frozone or just become frozen.
Yeah. I see your point. So yeah, I like occasional cold. Like when I open my refrigerator and freezer, I'm like, that's nice and refreshing. But let me close this quickly because I don't want to run up the bill.
No, let's get back
And-
on topic.
Yeah, okay.
Let's head over
Let's
to
methane.
the last thing
Worst
on the tier list. Boo!
Yep. Methane.
Boo! Methane.
I
Not a
feel
real solvent. What are you doing here?
yeah, I know.
Get out of
I-
here, bro.
I feel
Just
bad for methane. It isn't even polar, but unfortunately, it's just like so common and been used so much in all these cold planets that it's just kind of been de facto like welcomed into the solvent gang, and it's not fun. Yeah, methane. Also, it's a big contributor to climate change in its gaseous form. So you know what? Methane gets F tier. Yeah. So
Boo! Methane garbage.
so let's go to photosynthesis
Photosynthesis
and its alternatives. I should correct that to alternative because I only have one example here. There are there are more examples though. We're really just looking at
photosynthesis and its alternatives. We didn't bother to include.
Yeah, we included one alternative, but we only have a week to prepare this. Like we have 1 week, like between each
By
stream.
the way, this is our record for slides. We have 61.
We have a lot of slides this stream, so give us a break, okay? Basically, we're looking here at exothermic reactions that are not explosive, because that's not good. Exothermic reactions that life can control and that life can use sources of energy on its planet to produce energy for itself. That's pretty much the purposes of these reactions. So, we start with the classic photosynthesis. You know it, you love it. Photosynthesis, chlorophyll, green, plants. I think I've said all the words. Enough said.
Enough said. We've all studied it legitimately to death.
Yep.
7th grade science, or if you take accelerated science, still to this day. That's a joke that some of you might not get. But
yeah.
Photosynthesis has been a topic of science throughout like all of middle school.
Mm-hmm.
Maybe if you're unlucky, still in high school. It's a pretty basic concept, but schools love to use it as a way to explain chemical reactions.
Yeah, so I have
we have an alternative to it, which we're going to
talk about next. So first I have a 2-part animation for photosynthesis. So first we start with 6 water molecules and 6 carbon dioxide molecules. And then, bam, photosynthesis occurs and it becomes a glucose molecule along with 6 diatomic oxygen molecules. So that's pretty much how energy is made. There are more complicated photosynthetic reactions like that form different sugars like fructose and stuff like that. But this is just basic photosynthesis we're looking at. This is what you get. It's activated by sunlight. That's what gives it its energy to occur. And that's photosynthesis. So our alternative, chemosynthesis. Chemosynthesis is tried and tested. It is actually used on Earth. And some scientists say that
it works.
It might be like how life first started. So we have like in the ocean, there are deep sea vents. And this is like so deep in the ocean that there are no plants because there's no sunlight, so no plants, and no photosynthesis. So how does life get by in the ocean around these vents? Well, they use chemosynthesis, which I'll show you. I have another 2-part animation. Again, photosynthesis is a family of reactions, and so is chemosynthesis. So this is just a very simple reaction. You have, and this is why hydrogen sulfide might be redeeming. This is a redemption arc for hydrogen sulfide. You have 12 molecules of hydrogen sulfide and 6 molecules of carbon dioxide, and bam, chemosynthesis occurs and they form a glucose molecule, some water, and then just a ton of sulfide ions just floating around. That's chemosynthesis because these undersea vents spew out sulfur and energy, and it's a possible reaction for life. So it's pretty cool.
Yeah.
Scientists have actually researched, and I don't know if they confirmed it, but there are some suspicions that the deep sea vents where the life that exists down there, the bacteria, is actually independent in origin from all other life. So how abiogenesis and like our theories currently occur where there was like one bacteria that started it all, well, these life forms might not have started from that one bacteria. They might have had a different point of abiogenesis, which is pretty interesting. It means that life started twice on Earth instead of once. So chemosynthesis, it might just be the main thing on different planets, whereas it's kind of swept under the rug here. And then I'm trying to think of other alternatives that we didn't write down. Pretty much just any exothermic reaction. Look, okay, in defense, I would basically have to have gone to more than 3 pages. Like, I went through 3 pages, all I found was, like,
Come on.
Hydrogen, so
Man,
yeah.
like we got so many to
Yeah.
do. This is a 61 slide presentation.
Honestly, I mean, we're kind of going long, so you know what? I think it's good that I didn't find any more alternatives.
Yeah.
So
So why don't you get off our backs? Huh?
Yeah. Come
Thank you.
Come on. We'll
You wouldn't even have known about one.
Yeah, exactly. You wouldn't have known about one alternative
without this live stream.
Yeah. So you know what? I think we've done good. Just keep in mind that there are all other alternatives, and you know what? If you want to know that, you can do your own research. Come on.
Yeah. Let it be.
Yeah.
Gloria.
So we have terraformation is the next topic.
Next.
Terraformation. This is basically looking at all of these qualities of a habitable planet.
Yeah.
How do you take a planet How do you take a planet that doesn't have these qualities and just make it have these qualities?
If you go all the way back to the start of the stream when we talked about the classifications.
Yep.
Class K planets such as Mars, we said could be terraformed, go through an L state and then into an M state like Earth.
Yep.
So terraformation in layman's terms is basically taking a planet that cannot sustain life and then forcibly giving it all the characteristics of a planet that can.
Yep.
So making Mars more Earth-like or making Venus more Earth-like is terraformation.
Mm-hmm. And the origin of the word terra meaning earth and formation meaning formation. So that's where you get terraformation.
Yeah. Bam.
So let's look at the first aspect. We have temperature. So temperature, you might think if a planet is too close to a star and like we said with the Goldilocks Zone, if it's outside of the Goldilocks Zone, you might think maybe we should just take it and push it somewhere else and put it into the Goldilocks Zone. Well, if you thought that, then, Patrick Star is a good comparison for you. Basically,
we'll just take it and push it out of the way.
Exactly. The amount of energy it would take to move a planet is insane. And in the process, you would fry the planet and just completely destroy it, make it uninhabitable, even you would have no possibility for terraformation. Gravity Max does not condone moving planets, okay? Gravity Max does not condone moving planets. So, how would you change temperature? Well, it's really just a question of energy in versus energy out. So, how do you, get less energy for a hot planet or get more energy for a cold planet? You just put a giant shade or a giant, magnifying glass or mirrors or something. It was just magnifying glass was easier to draw here. So you just put that in orbit. And basically what it does is on the left, it's kind of obvious. We have another 2-part animation here. I'm going to go to the second part. When you have your shade over your planet that's too hot, it becomes colder because less light is hitting it. And when you have your magnifying glass on your planet that is too cold, it thaws it out and makes it warm again. Or not again, maybe it never was warm, but it makes it warm. Let's see, I'm trying to think here. Oh yeah, so you might think it's really difficult to build a giant shade or a giant magnifying lens in orbit, but honestly, you thought you could move a planet. So when it comes to difficulty,
Superman did it in the comics.
Yeah.
We don't condone
moving
anything
planets.
Superman does.
Yeah. Okay, because when it comes to on the scale of difficulty, and keep in mind this is going to be a logarithmic scale. If you have moving planets as a 7 on just scale of difficult things you could do, building a giant thing up in orbit, just a giant sheet pretty much for a shade or a giant thing of glass for a lens, that's got to be a 4, and then 1 + 1 = 2 is our baseline 1, or 0 actually, for our logarithmic scale. And hardest thing in the universe, I would say moving a galaxy, that is number 10. It is possible though, and you can do it. It's just very gradual. But that's topic for another time. Yeah, you can move a galaxy. But anyways, So the next topic, Magnetosphere. So, as we said before, you just need a magnetosphere. So what do you do if you have a planet that does not have a magnetosphere? Well, you make your own. Just throw it up in orbit right there. Pretty much just chuck an MRI machine at the Lagrange, the first Lagrange point of a planet.
Can you hit percent and then percent again real quick?
Oh yeah, sure. Oh no.
Okay, there we go.
He's here.
Continue.
Anyways, what was I saying? Yeah, MRI machine, just a really strong electromagnet that you put between the sun and the planet that you want to have a magnetosphere. And then the planet is protected from a lot of the sun's deadly rays. That is what we could do with Mars. There is a paper by some NASA scientists on it. So if you want, you can check that out. And 2-part animation again, makes the planet habitable. Also gets rid of Magneto because you didn't put it on both slides. Yes. Good riddance. Oh my gosh. The Spectre. Anyways, so that's Magnetosphere. It's a pretty simple one. So the next one is material.
I believe.
The next one is material, right? And this is a bit more complicated, and it isn't a permanent thing. It's a process. Whereas the last ones is like chuck a mirror in there and just leave it there. And like throw an MRI machine in there and leave it there. But for material, you don't need to keep constantly adding material. You just need to add the right amount, you know? So sources of hydrogen. If you don't have enough hydrogen, then you cannot make any solvents, right? Like we said, the solvents are important, and all of them contain a ton of hydrogen. Hydrogen is a really important atom, and if you do not have it, then you need it. But thankfully, all stars are full of just so much hydrogen. So if you need hydrogen, you can get it from a star, and you might think, how do I get it from a star without burning? Well, it's a process called sun lifting, or star lifting. And on our like scale of difficulty, I'd put it at like a 6. Okay, you can basically, it's complicated and it's probably good like for another live stream, but basically if you just put a mirror right over the sun and reflect its light back at it, then you're gonna make the hydrogen on the surface of the sun too hot, like hotter than it already was, and it's just gonna evaporate off. And so then if you collect it and throw it at your target planet that does not have enough hydrogen, then it gets hydrogen. Also, you have, for nitrogen and oxygen have their ammonia and water solvents, and those solvents are often found in ices. So in astronomy, the term ice actually means a mix of water ice, ammonia ice, methane ice, but if you want to specify water ice, you actually have to say water ice in astronomy, or else people won't know what you're talking about. So if you use comet dust, comet tails, and just throw it onto the planet, you'll get some water, oxygen, nitrogen, all the good stuff. Same for sulfur and phosphorus, but with asteroids, you'll find them in more mineral compounds than in icy compounds. So you can get some dust, sprinkle it on there, and then, bam, you get your habitable world. So yeah, that's it. Anything else to add?
Are we on our final thoughts now?
Yeah. So first and foremost, before we conclude this video, I would like to thank you and thank Daikaiju Productions for coming and being on our stream. Yeah, thanks for coming. You've got an awesome channel, and those stop motions, how long do they take to make?
Stop motion is an incredibly intensive process. Mm-hmm. I mean, you have to take a picture for each frame.
Yeah.
So it takes much longer than a normal video, like thousands of times long.
Yeah.
He definitely puts a lot of effort.
Yeah, lots of respect for that.
Just checking him out.
Yeah, like I thought it was too hard to like make slides and produce a video and do video editing, so that's why I just kind of defaulted to live streams instead. So yes, lots of respect for the commitment and like all the energy it must take to make these stop motion animations. So you should definitely check them out. They're really cool. So yeah, so concluding this video, we've got our classifications of planets, right? We went through the Star Trek unofficial classification that we're still going to use, obviously, because it's fun.
Yeah, come on.
We're going to use the good ones. I would say if...
I'm definitely using Y planet.
Yes, exactly. Z planet, X planet.
Yeah.
We should probably stray away from the gas giant classifications, though, because
Yeah.
those are garbage, gotta say. So then, what else? So then we had our qualities of a habitable planet. You've got your temperature, your Goldilocks zone. You've got your materials in the atmosphere and in the ground. You've got your magnetosphere. So I think this was a pretty fun video. And then you
I
also...
definitely had fun.
Yeah, so then you also have the concept of terraformation and the process of terraformation that you would have to use to make a planet habitable. What do you think about that? It's a really long process, you know.
Yeah. Definitely.
Like-
I don't know what years could be possible.
Yeah, it would take a really long time,
but
centuries.
It's pretty far off. I'm not even sure if they have Dune.
In Dune they don't have it?
And like I said, Dune was set 8,000 years into the correctly.
Yeah.
I have the book. I can.
Yeah.
Have it, but I'm lazy.
Yeah, well, terraformation, it isn't even a highly scientific, it's not even a really high-tech process. It's just a brute force process, and it just so happens that humanity does not have that force right now. It just takes so much energy, so much material, and such a long time. So, anything else on terraformation?
Yeah.
Nope. Okay.
So... is that all?
Well, there's one more thing.
Mm-hmm.
What's that?
That you can terraform a planet, but if you do, you have to plan it in advance.
Ah!